Alright, welcome back guys. We're going to be starting the first material of Module 2, so namely 7.1. And this deals, as you can see, with symmetry. Okay, so pretty sure everybody has an idea of what that word means. And there's, you could probably look at things. I've got some examples here. We are surrounded with symmetry, guys, in the natural world. And even a lot of our architecture exhibits symmetry. It's very appealing. It almost seems to be in the fabric of life itself, symmetry. So, for example, my body, if I do, I think it's called a transverse of my body, then I'll end up with two essentially equal or mirror parts, right? I have two hands, I have two arms, I have two legs, 2 feet, I have 2 ears, 2 eyes, okay. But I wanted to look up just a general definition of symmetry, and then we're going to look at a more mathematical definition. And really, symmetry, guys, in my opinion, can really only be defined mathematically. And I'll tell you why here in a minute. So I looked up on Google's AI enhanced search here, and it says symmetry is the property of an object being invariant or unchanging under a specific transformation, such as a reflection, rotation, or translation. So what that means is this image right here, this butterfly, it is unchanged if you rotate either of these wings about this axis right here. Okay, and then it goes on to say this concept is found across nature, mathematics, art, and science. There's a lot of symmetry in art. Okay, and then there's different types of symmetry. We'll talk about that more specifically. But when we look at this image right here, guys, and I say it's symmetric, or let me go to my notes. We look at this image of this butterfly, we can say that it's symmetric about an axis, okay, and the axis goes right through the middle of the butterfly. And really what this means is that any point on this butterfly's wing is basically, think about any point being defined by an x and a y coordinate. That would define a point, okay? We could even use like a third coordinate to designate the actual color of the point. But for that point to be reflected to the other side, or for this wing to essentially remain unchanged, its x coordinate would have to be reversed. It would have to end up being negative, or vice versa, okay? Any point over here, you could say, well, all these points, they're defined by negative x values. To end up over here, to be reflected about this axis right here, those x coordinates or values would have to change sign, essentially. Okay? And then we see this figure right here that has symmetry about one axis and also symmetry about another axis. And so what happens here is, like, if I take this arbitrary point right here, let me zoom in. This arbitrary point, okay, it's kind of dark green. For it to actually be reflected down here, both its x and its y coordinates would have to change values. Its x changing value would put it over here. Its y changing value would put it down here, okay? And then we've got a couple of man-made or architectural examples that exhibit symmetry, right? This bridge reminds me of the bridge when you go across the Mississippi River, if you're headed to Memphis along I-40. And then this temple or gazebo-looking structure, it has symmetry as well. And also even the landscaping is symmetric, okay? All right, so let's go on. and define kind of what this means mathematically. I've already kind of hinted at it, so you could find a multitude of things that have symmetry. All right. Even look at this picture behind me, guys. This is a picture that I took. Well, it's a time lapse of a lunar eclipse. Okay, that I took, I think, back in 2019, maybe. So I took a bunch of pictures of the moon at even intervals in time, and I picked out a few and I made this. Well, there's some symmetry exhibited here. Okay, there's even some symmetry through time. So you could say at the beginning of the eclipse, the Earth, or the moon rather, was basically the same as it did so many minutes or hours after the totality of the eclipse. Okay, so that's just an example. Another example. All right. Okay, well, here we are going to consider three types of symmetry. Symmetry with respect to the x-axis. Okay, and when I say here, I'm referring to functions. We're going to be focusing on functions. What functions exhibit symmetry, and what types of symmetry do they exhibit? Okay. So here's an example. Now this is not a function. Okay, this is just a relation. This would actually be the equation right here. Instead of y equals x squared, which makes that parabola, this is x equals y squared. That's why this is rotated. Okay. And so what we see here is, if you take these 2 points right here, they have the same x coordinates, namely 4, but they have opposite y coordinates. Okay, and you can see that more generally. The x coordinates will stay the same, but the y coordinates are additive inverses of each other. And so that gives us what we refer to as x-axis symmetry. Okay. In other words, if you were to rotate one piece or one side of this parabola along the x-axis, the other side would line up. Okay, this side below, this piece below the x-axis, if we were to rotate it, it would line up on top of the piece that's above the x-axis. So that's an example of x-axis symmetry. Now, functions cannot have x-axis symmetry, because what you'd have going on, as you can see illustrated here, is you've got 2 different points. They both have the same x coordinate or the same input, but they have different outputs. Okay, so essentially what you would have, or what you have, is, I forgot to plug in my is you would have this x would be your input, and then it would be mapped to 2 different outputs. Okay, so no function is going to exhibit x-axis symmetry, but there's a lot of relations, just relations between x and y, a lot of equations, in other words, that if you graph them, exhibit x-axis symmetry. Okay, all right, and then the other type, and functions will have this type, y-axis symmetry. Okay, and so we see here, this is a quadratic function, isn't it? It's a quadratic polynomial. Y equals x squared minus 5. Okay, so this is similar to x-axis symmetry, except the opposing or mirror points, the y coordinates are the same. See, 4 and 4. But the x coordinates are opposites, -3 over here, and then +3 over here. So that's what creates the y-axis symmetry. Now, for quadratic functions to have y-axis symmetry, they have to be centered on the y-axis. Okay, if they're shifted left or right, they're not going to have y-axis symmetry. All right. And then the last type of symmetry that we're going to talk about is origin symmetry. Or in other words, symmetry with respect to the origin. There's an example up here. This image actually has X, Y, and origin symmetry. Okay. It exhibits all three. But anyway, so what does symmetry with respect to the origin means? Well, the origin is the center point here. So it means for two opposing points, or two corresponding points, to be symmetric with respect to the origin, not just their x's, but also their y's have to be opposites. Okay? So both x and y have to be opposites. And so here's an example right here. This point, its x-coordinate is -3 and its y-coordinate is the square root of 7. I want to keep saying opposing. Its corresponding or symmetrical point is down here. And notice, now the x-coordinate is +3 and the y-coordinate is negative square root of 7. Okay? Now again, this one is not. A lot of this one actually exhibits both x and y symmetry as well. That's actually what it means for something to have origin symmetry. It exhibits both x and y symmetry. Now, as you can see, this is not a function either. But this is the equation that describes. Okay. And what happens is, for any given x value, except for like maybe this very edge point and this edge point over here, each x value is going to have two different y's. Okay. So that's why this one would not be a function, but it does exhibit origin symmetry. Another way you can think about it is if you can take one piece in one of these four quadrants, so I'll arbitrarily choose this piece right here. If you can rotate it about both the x and the y-axis and have it line up on this other corresponding piece in the kind of opposing or diagonal quadrant, then it has origin symmetry. Okay. All right, this is not a real long section, guys, so I think we'll get through it in just one video. Alright, so example 1. All we're going to do here is just identify the type of symmetry that we see exhibited. Alright, so the first one right here. This one has y-axis symmetry. Okay? And the reason is because if I take this left piece and I rotate it about the y-axis, okay, so you're rotating it vertically or along a vertical axis, then this left piece would lie on top of the right-hand piece. That's what it meant in that definition, to remain unchanged, okay, essentially through transformations. Because when we rotate it about an axis, we're transforming it. Its essence is staying the same, okay. Now, what about this next one? This one is exhibiting origin symmetry. The reason is because it has both x and y, or it doesn't have both x and y symmetry. It does in a sense. If you take this left-hand piece, let's say we rotate it about the y-axis first, then it would end up over here, okay? And then let's say we take that piece and rotate it about the x-axis, then it would end up down here, okay? So it ends up in the diagonal quadrant. So if every point on here, when transformed or rotated about both axes, forms the piece in the diagonal quadrant, then you have origin symmetry. And then finally, this one is kind of like a sideways absolute value function. It's actually something like this. Instead of y equals the absolute value of x, this is x equals the absolute value of y. And then there's probably like plus some constant that shifts it over here to the right. But anyway, nonetheless, this exhibits x-axis symmetry. Okay, this is symmetric about the x-axis, which is the horizontal axis. All right. Now this one is not a function, though. This is not the graph of a function. These other two are, though. This one right here, guys, is actually a polynomial, the graph of a polynomial. So it could be something like a polynomial that has an x to the fourth in it, or something like that. And then this one could be, this one I think is probably like a cube root function. So anyway, all right, so now let's go on. All right, so functions can only have two types of symmetry. They can't have the x-axis symmetry, see here, because they wouldn't pass the vertical line test if they did. All right, so they can only have y-axis symmetry and origin symmetry. And so functions that exhibit either of those types of symmetries, we give them names. So a function that is symmetric with respect to the y-axis, we call it an even function. And then a function that has origin symmetry is referred to as an odd function. Okay. Now there are mathematical definitions. Okay, we don't really get into that in this class, but there's a way that if you have the function, you don't have to look at its graph to determine the type of symmetry that it has. Okay. But anyway, all we're doing is just looking at the graphs. Alright, so we want to determine visually whether the function is even, odd, or neither. Okay, so this first one right here, this, you can see it's a parabola, isn't it? It's upside down. So that means this probably corresponds to a quadratic function. Well, it is even, and the reason is because it has y-axis symmetry. Okay. So a quadratic function, guys, that's centered on top of the y-axis is an even function. Okay. That just means that if we change the sign of the x that we plug into the function, the y-coordinate is going to stay the same. What about this one here? This one. Well, it's definitely not even because it doesn't have y-axis symmetry, but it is odd because if you take either of these pieces and rotate that piece about both axes, it will line up on the corresponding piece in the diagonal quadrant. Okay. We actually worked with some functions that were odd, so y equals x cubed. Okay, that's part of the reason they say that they're odd, okay, because that's an odd exponent. And then, you know, the classic or the basic quadratic function is just y equals x squared. And this is an even exponent. So anyway, now this doesn't correspond to y equals x squared. This is a cube root function. So it's similar to a cubic, but it's the inverse of it. But nonetheless, it's odd because it exhibits origin symmetry. What about this one? We've seen a graph of this before. This would be the function y equals 1 over x. Okay. This one is odd as well, guys. Because this piece right here, if you rotate it about the y-axis, it would end up over here. And if you rotate that piece about the x-axis, it will end up right here, okay, in the diagonal quadrant. So that is an odd function. And then finally, we have this absolute value. Well, I think actually we have a couple more. We have this absolute value function, y equals the absolute value of x This is even because it's centered on the y-axis, and each piece is just a reflection about that y-axis. Okay, this is an even function. And guys, we're going to talk about symmetry more when we start studying quadratic functions or parabolas, because they will all have symmetry. It may not always be about the y-axis, though. If the quadratic or if the parabola shifts to the left or to the right, you can think about that axis of symmetry shifting as well. And that's something that we'll have to actually describe when we get to that section. All right, let's look at a couple others. All right, this fifth one. This is the graph of a function, but it's a function that we haven't studied yet. It's actually a square root function. But because it only exists in one quadrant here, it doesn't have any kind of symmetry. Okay. Anytime a function only exists in one quadrant, it's not going to have any type of symmetry. So here we would actually say that this one is neither. Okay, it is a function, of course, but it's neither even nor odd. That's the way you would express it. Okay, neither even nor odd. And then what about this last one? Well, the last one, guys, is sort of a trick question. It's not even a function. Okay. So we can't even then say whether it's even or odd. It's not even a function. It does, however, the relationship between x and y that this graph represents, it does have x-axis symmetry, just to point that out. Okay. All right. Well, anyway, I don't think this section is too challenging, and it only took us one video. Okay, so that's nice. Alright guys, so start thinking about symmetry. Where do you see it in your everyday lives? Think about an automobile. An automobile has symmetry, right? So many things have symmetry. Think about an open book. When you open the book, like right in the middle, isn't it in a sense symmetric? Think about my little container right here. This has symmetry, right? There's an axis. The axis actually cuts like right through the middle of it. And every single point on here can be defined by just simply being a distance away from that axis. A distance, and then it has a specific color. But anyway. Alright, well, I'll see you in section 7.2 then.